what I'm saying that initially we don't have this one, right? Now we have this one. So this one is the known degree of freedom, right? 0. We don't have any displacement at this degree of freedom. So if this one is 0, we eliminate this row column associated with this, right? It will become more like the first one we had. This one, as you know, so it's gone, right? You know displacement. So this row and column will be eliminated, but not that eliminated. You multiply by the known displacement and push on the known side. But the size of the matrix will become just like the original. What else? This one, originally you have 0 displacement here, but now we prescribe displacement, so you get some prescribed displacement multiplied by the whole column, and then we eliminate rotation 0 and 0. So the thing is, you actually end up with exactly the same matrix. Am I right?
So 2 additional vertical U11 and U12.
Yes, I know.
At the top.
But this and this are the same, right? I remember that last time I put this one here, alright,
So, yeah.
which is the same as this one.
But this displacement adheres to the beam as well.
I know.
12 UL3.
But since due to that elimination, then that's all gone. I added there. But when you enforce boundary conditions, since it does not move,
But
so
once we apply for Lagrange, then what will happen?
for Lagrange it will be different. But as I get informed, both Lagrange and row and column elimination turns out to be 0 determinant, right?
Yeah.
0 determinant, but the matrix, the K matrix, is still the same. Am I right? For the row and column elimination. From doing all of this, you have the same matrix. We get rid of this vertical. We added these two, okay? We added these two, so matrix, it originally before you have maybe n by n, now n plus 2 by n plus 2. We have n plus 2 by n plus 2. The point is that these two more are associated with the boundary condition, right? Because we know that at this node there is no vertical displacement. So the two additional row and column, okay, maybe one row and one column, will be cancelled out, eliminated by enforcing this boundary condition. If I do it this way, this is what we have on Thursday. Alright, this matrix we had on Thursday. And then you have 2 more rows and 2 more columns, okay? Okay, don't be so serious about the location of row and column. It might be somewhere, but I just push them over here. My concern now is that if you enforce this one, this boundary condition, then I will eliminate 1 column and 1 row. Am I right? Yeah? Correct? Just row column elimination. And the other maybe additional degree of freedom here, you know. When you know, you multiply that known to a whole column, push it on the other side, okay? Push it on the other side, and also this one, you will not make use of it, okay? Because this row is associated with the unknown on the right hand side, because it is the boundary condition. You have the reaction, so you will not make use of this row. So finally, we end up with this matrix,
The same.
and this matrix, exactly the same matrix, has it is capable for the inversion last time. So I just wonder why it is not possible for you having a determinant equal to 0. That situation should not happen. Is it the same? Huh? Did you come up with the same thing I mentioned here? Your system matrix. Is it like this, or you have a different system matrix? Same? Not the same?
At the first time, same.
Huh?
At the first time, same. But after discuss with my friend, I change. I'm not sure about it.
First time it was the same.
Yeah.
Okay, and talk to friends and then you change. And okay, same as your friend. But okay. But end up you get that. And if you have that, then the solution is possible. But for now, anybody get solution? Non-zero determinant? Any?
So what for Lagrange is Lagrange?
Lagrange? Lagrange, so you have 2 more rows, 2 more columns, and then you enforce the Lagrange multiplier. So you have 2 more Lagrange. Initially you have how many? I don't remember, 4 Lagrange equations, right? Then you add 2 more, so you have 6 displacement conditions. Straightforward. Yes, because we have 2 more degree of freedom to enforce, we have 6. But the rest of the thing, I think, mostly, yeah, almost the same. Okay. So, in fact, if you don't want to waste time, you know at first hand that this degree of freedom will not active, right? Will not be active because it is a support, and I'm not prescribing any displacement to be supported. So you may not cast up your system matrix to include this one. You just need to include this one. That's possible. Because you make this one, then you eliminate this one. Alright? So it might not be useful for you at all. So you just add this one, and this one, when you add in the row part, will be just gone. So the column part will be the part that really use because it will be multiplied by the load displacement and pushed onto the right hand side. So that's how it works. Anybody can turn in? Wow. Let me ask you, what have you done in there? So you come up with the zero determinants. Can you?
You want to discuss one problem?
Huh?
You want to ask one problem?
What? Just make sure that the prescribed displacement is correct, right?
Yes, this is 0.5.
So that minus 5 because it go down. So Lagrange work for you. Row and column elimination
No.
does not.
Does not.
But the way, okay. Huh? Couldn't come, okay. Minus 1, minus 1, minus 1, minus 1, minus 1, okay. Okay, some problem with the inverse. So just Lagrange, but row and column elimination works or not? I requested you to do both, right? Row and column elimination and Lagrange multiplier. Does that work? So try just Lagrange. Your case, it works. At least Lagrange works. I think the same. If you have such problem, you can get MATLAB to help. Sometimes the Excel inversion might not be that good. Okay, not a number, so it has a that zero determinant problem. But in this case, you can inverse.
You can inverse this one. The same thing.
So let's check. If the Excel cannot, try MATLAB. Sometimes MATLAB do some kind of pivoting, arranging the matrix a little bit, and then it is possible for getting the inverse. But the matrix is. I don't see, not for now, quick. I don't see anything wrong for now.
ไม่เป็นไรแล้วเราเอาเปลี่ยนตัวแทนว่ามัน
Why try the pen? So everybody just do Lagrange multiplier or what? I don't.
Row and column elimination, but I didn't get that.
Okay, but what went wrong with that? What went wrong with your row column elimination? But what did you end up with the matrix we had on Thursday? You did. If you end up with that one is for sure can be inverse. Okay. So can you inverse it? And not? Okay. So let's put it this way. Okay. The problem with the Excel, why can we inverse? First of all, your determinants is equal 0. Okay. And why would that cause a problem to us? Okay. The thing is, Excel is not as smart as MATLAB. It does everything pretty straightforward. So for this kind of problems, it may not do the pivoting. Pivoting means like changing some row and column configuration such that the inverse is possible. Now you have -1, -1, -1, -1, something like this. This is all 0. Okay, this is the case. But anyway, for row column, I don't see any possibility that leads to such problems. So we'll make sure that it would work and turn this in tomorrow. Okay. Have all this whole work turned in tomorrow. Then if it's like this one, okay, -1, -1, -1, 0 elsewhere. So when you calculate the determinant of the matrix, you multiply like this, right? Right? And then you multiply this direction, and then this front part minus that part of that. Okay. The problem comes when, okay, you have lots of 0 here and lots of 0 there. Sometimes, okay, you have 0 here, so you get 0, 0, 0. Okay. So 0 on the back and 0 on the front, and then finally you get 0, which for some case, maybe for this case, if you want to end up with some finite number of determinants, you can do some kind of rearranging the row and column. So if we arrange the row and column such that this number -1 is aligned in this fashion. The thing is, it is possible, right? You can switching things around. If you switch the column up or down, your row will be switching up or down accordingly also. So you can set up at least this line, the line of which the numbers that is staying on are non-zero, and then you can come up with some finite number of k. So Excel will not help you doing this. So whatsoever it has from your input, then it will calculate the determinant based on this matrix configuration. So there is no pivoting. But I guess MATLAB might help you do that. Okay, so throw the number into the MATLAB for the Lagrange multiplier method, and copy all of this and paste into MATLAB. I think it would work. So your Excel, what you have from Excel sheet, paste it there in MATLAB and get it to inverse. And you will see, I think you will overcome that problem. But that's the only bad things about the Lagrange multiplier technique, because it has a lot of 0, and sometimes even MATLAB or some good solver undergoes this situation where you enforce a lot of boundary conditions. You have a lot of 0, and then the determinant is 0, so you cannot inverse the matrix. That situation could be the problem sometimes. Okay, so submit tomorrow for this homework. I don't think that aside from this inversion problem, this part shouldn't be your problem. Okay, so overcome these two and then turn in tomorrow. What time? In the morning. Yeah? Drop it and the secretary of the structure, Chanya. Okay? So UGPG, everybody is drop it there at my secretary. What room? Same room as Dr. Bui. Okay. I don't remember the room number. Do I have that map here? Oh yes. Okay, so anybody has any more comments and problems relating to this, the last homework? No? Okay, so that's good. So tomorrow I will not see some guy approaching me and tell me that I cannot do this. And I will say, okay, I ask you if you confront with any problem yesterday, why don't you raise your hand and tell me? Okay, so no? Alright? Great. Alright. Now I think we are almost done with the manual. Okay. It is the bridge between the manual and computerized structural analysis because okay, you use some computer, but you are not doing the computer programming now. I think you mostly understand how the computer thinks at this point. So how you start, you get stiffness matrix, okay, you account for rotations and then you plug in the entries from your element stiffness matrix into the system stiffness matrix. You get the force, okay, force vector, you inverse, you multiply, okay, whatsoever boundary condition techniques that you might use, okay, it's your choice. And then you do all the things, you get the solution, okay. So we are at that point now. So now we will talk about how to tell the computer to do all of these things, which is tedious. We just did 6-member structures, right? That frame, just 6 members. Okay, it takes some time adding things up, the matrix of the size 10 by 10, or in other words, you have 100 entries in there, and